Today we're going to be discussing our first topic in engineering mechanics. And engineering mechanics is broken up into several different subtopics. The one that we'll be looking at today is going to be statics. And in statics, we will be analyzing the forces acting on stationary bodies. So we will only be concerned with forces and distributed loading. We will not be concerned with things like acceleration or the change in position, things of that nature. That is what statics means. It means that the particle or collection of particles under analysis are not going to be allowed to accelerate, so they'll be fixed in place. A good example to start is the simply supported beam. And I think it's best to lead by example. So for a two-dimensional body in equilibrium, the following is true. And so with these three things in mind, we can start with an example. And so what I'm going to say is that a horizontal beam is supported by a pin at A and a roller at B. So pin and rollers are different types of supports that you might see on bridges and other civil structures. And their job is simple. It's just to support the beam. You might think, why would you want to put a beam on a roller? And this is actually to allow for thermal contraction and thermal expansion as climates change. You can imagine that the effect that thermal expansion or contraction has on a large body is quite significant, and therefore we need to allow the beam to contract or expand without crushing or breaking apart. And so I imagine that here there is a pin going through like into the page. And what that's going to do is, well, let me finish drawing my forces as well. So we're also going to say that 1.5 meters from the left, let's do it 1.5 meters from the right. So we are going to have a force of 600 newtons. We'll call that P, the load force. We'll say that the entire length of this beam is 5 meters. We have a pin support here, and we have a roller support here. What is the significance of the pin in the roller? Why do we need to know that? Well, these different supports are going to constrain the motion of this beam. For example, the roller support is going to stop the beam from accelerating in the downward direction. It's going to keep it stationary in the y direction. And by the way, it's always important to label our coordinate system. The pin support is going to do the same thing. It's going to support it in the vertical direction. It's going to keep it from accelerating in the vertical direction. The roller support is not going to do anything in the horizontal direction. There's no constraints there. So there's no support reaction in the horizontal direction for the roller support. However, we cannot say the same thing about the pin support. The pin support does in fact constrain the beam's motion in the horizontal direction as well. In fact, in all directions, so horizontal and vertical. What about the moments? Well, it looks like the roller support does not permit any rotation about it. However, the pin support does. So the pin support allows for a reaction moment and reaction forces in both the x and y direction, whereas the roller support supports only forces in the y direction. Redrawing the diagram, excluding all supports and replacing them with their reaction vectors. I'm going to call this point A and this point B. This will be the reaction force in the vertical direction and the reaction force in the horizontal x direction. Similarly, we'll have point B, and we'll have just a vertical reaction force, right? Because that's the roller support. It does not support the beam in the horizontal direction. What we can start doing now is writing our equations that I wrote down here. We can now apply these to a two-dimensional body in equilibrium. That's what we're analyzing here, a beam in equilibrium. I'm going to write the equations. We can often define the positive direction like so. And when I look at this diagram and I look at my blue arrows, the sum of my forces in the x direction has to equal 0. So I have AX, and that's it. So that gives me one of my reaction forces immediately. There's 0 reaction force in the horizontal direction at point A. But let's look at the moment equilibrium about point A, right? Because we can also rotate about this point. And we'll call this MA. The sum of moments, and I'll define this way to be positive, about point A must equal 0. Well, we have one force. First of all, look at the forces at A. The moment is defined as force times distance, but the distance for these forces, the distance associated with these forces at A is 0. So the moment generated by the forces at A, AX and AY, are equal to 0. So I need only be concerned about this 600 Newton force and this vertical force BY, because they are some distance away from point A, and that's the point that we have chosen to analyze. And we'll actually talk about why. You might already see exactly why we did that. Anyway, let's do the P force. This is going to be P times, what's the distance? It's 5 minus 1.5, so that's 3.5 meters away. And this is negative, right? Because it's going to rotate this in a clockwise fashion, and I've defined counterclockwise to be positive. And then so B is going to do the opposite. So it's going to be a positive sign, and we'll have the force, By, multiplied by the distance that it is away from the point that we have defined here in our subscript on the left-hand side of this equation for the moment. It's 5 meters, right? And so we have an expression for the sum of moments in A. Let's find By just using this, because we actually, that's the only unknown here. We actually already know P is 600, right? And so if we solve this equation for By, remember this has to equal 0. Sum of moments about any point on the body has to equal 0. Doing some quick algebra. So we get a force of 42 newtons for the reaction force at location B. And this is obviously upward, right? Because it's positive, and that's actually how we defined it in our free body diagram. So if I got a negative number, that would just mean that the force was actually acting in the downward direction, and I just drew it wrong on the diagram. So the sign is very telling in these problems. What's left? We still need to get AY, okay? So how do we do that? Well, it looks like the vertical forces, if we look at the sum of the forces in the vertical direction, similarly, I can define my positive convention just like that. We have just AY, we have this downward force of 600 newtons, and then we have the upward force of BY. So the equation for this is just AY plus BY minus 600, and this must be equal to 0 since the mass is not accelerating, right? It is in mechanical equilibrium. That is the definition of mechanical equilibrium for a two-dimensional body. What do we do here? Well, we already know BY, and really so this just boils down to AY equals 600 minus 42. And we get AY is equal to 558 newtons upward. We have AX, we got BY, we got AY. So we've solved for all of the forces on the beam using this static analysis. And so this has been a first lesson in engineering mechanics statics. All right. the analysis of forces on an object, and we'll typically call the object a particle, or it will be a collection of particles. And then we'll do a force balance using this free body diagram. And then we just employ our kinetic equations to solve for all of the forces on the beam. So I hope this has been helpful. That'll wrap it up for this video. If you have any questions, please leave them in the comments. If you would like me to clarify anything or cover anything in the future, also leave that in the comments, and I would be happy to oblige. Thank you for viewing. Have a wonderful day.